do that at the start too. So Ben and Jan are both, I'd say, relative newcomers in the sense that we have a few old hands to the Exascale Lab, which is a team with students from both applied math and statistics, where Jan is, and computer science, where Ben is located right now, or at least is studying. And so it's in that sense sort of slightly cross-disciplinary inherently, and we're interested in a lot of things to do, especially with the system software on large scale, so HPC systems, and in particular related to the programming environment. So programming models and how they're implemented, and you know, what we can learn from them. And so Ben and Jan are both completing their degrees. They're both master's students, and this is the end of the road, which is a bit sad, but of course it will be exciting, I think, for, you know, going forward, right? For new horizons. And they have been two of the pioneers on a new system, which is also a new kind of architecture, at least for the United States, and I'll leave it to you to talk about it. And of course, whenever you try something that's really new and in many ways unproven, even small progress sometimes is quite a big effort, right? So so don't be fooled by some of these things. Sometimes there's a lot of work behind things that perhaps on a, you know, common system and common platform with tools that are being used by millions of people would be very different. So so being pioneers is always exciting, but it's challenging. So I'm going to hand over to you to talk about some of the things that you've done and learned this semester in the last month or two. So it's all very recent. Thanks.
Thank you.
Thank you.
All right.
You ready, Jan?
Okay, yeah, Ben, you want to start it?
Yeah, okay. Awesome, I can see your
Yeah,
screen, so.
Doing well? Anyone?
So yeah.
Okay.
So awesome. So for those who don't know, I'm Ben. I'm here with my friend and colleague Jan, and we'll be talking about our experiences studying OpenMP behavior on the A64FX processor. There's probably just a lot in that just single sentence, but hopefully this presentation will help break it down. Next slide, please. So here's our agenda. We'll be discussing what the A64FX chip is and what Okami and Fugaku are, in addition to what vectorization is with reference to system software and processors, and what it means for HPC applications. We'll also be studying what OpenMP is and how it relates to our study, or to our experiences. And we'll, in the second half of the presentation, will be a case study with two different applications, Swim and Pennant. And then we'll also compare how they perform across different compiler tool chains. So next slide, please. So we'll start off with the A64FX chip, and that is the latest ARM processor. ARM being a hardware architecture compared to, say, Intel or AMD, made by the Fujitsu Corporation out in Japan. One processor is made up of 48 compute cores. So think of like the 36 cores on an Intel Skylake processor that you've seen on Seawolf. And here we have 4 core memory groups of 12 cores each. And I'll explain what that means in a couple slides. But the idea is that it's a way of being able to lay out memory and resources. Each node has 32 gigabytes of high bandwidth memory on chip, so to speak, where you can have maximum bandwidth or data transfer rate of 1 terabyte per second. So to kind of put that in perspective, think of the solid state drive in your computer and put it on steroids by a lot. The additional part of the A64FX chip is that with the latest ARM instruction set, it comes with this notion of scalable vector extension instructions, or SVE instructions, where the A64FX chip allows a bit vector width of up to size 512, and I'll explain that in the next slide as well. Basically, these instructions help optimize HPC applications and vectorize various structures such as loops in code, or even more complex operations. So on the next slide, we'll discuss what SVE instructions are. So next slide, please. The idea behind the scalable vector extension, or vectorization in general, is to take an item such as a loop and turn it into a single operation inside machine code that works on multiple components simultaneously in the hardware without even having to parallelize code with using libraries such as MPI or OpenMP. The bottom line with this is that it helps with executing, say, fewer instructions where you normally have more, like say many, and it's generally geared towards faster, just more efficient code and execution. So next slide, please. Here's essentially a breakdown of the A64FX chip, or at least one of the two versions. There's the FX700 version, which features just these 12 cores per memory group. Each group has their own portion of 8 gigabytes of this high bandwidth memory. The FX1000 chip, which we'll get into in a minute, has up to 1 extra core per region for OS operations. So it's not really used in the major computation. Next slide, please. So diverting a bit from the A64FX chip, we'll go into what OpenMP is, and it stands for Open Multiprocessing. These days, it is a parallelization specification for single node computation. Meaning, if you want to run an operation, say on a single node, compute node on Seawolf, for example, OpenMP would kind of be the way to go, ideally. And it's primarily used in C, C++, and Fortran applications, defined by this hash pragma OMP something directive inside C and C++ code, or exclamation point $ OMP inside Fortran. And this is kind of the second half of what we'll be studying with the A64FX chip. So going with that, let's scale up by a lot on the next slide, and we'll talk about what Fugaku is. Next slide, please, Jen. So I more or less kind of ripped this off from Robert's slides, and thank you, Robert. Fugaku is the world's fastest supercomputer located in Kobe, Japan. It is the first machine. First off, it runs on the A64FX processor. The processor was kind of designed for this computer, and is the first supercomputer to take the top position in all 5 of these major benchmarks, ranging from Green 500 for energy efficiency to Top 500 and Graph 500. Both going in different directions of either graph processing algorithms and execution, or just general floating point operation calculation. It's comprised of almost 160,000 nodes across 7.6 million cores. And this kind of gives the idea of like how powerful this processor can be if it takes the top rank in all these benchmarks. On the next slide, we'll scale back a bit and jump back over to the US with Okami. And Okami is an NSF testbed that is available for researchers worldwide and is the first deployment of the A64FX processor outside of Japan. There's another cluster off the University of Edinburgh, but we're the first, so kudos to us. Like Dr. Chapman said, Yan and I were part of the team that ran and helped create acceptance tests for the Okami cluster. And back in December, we helped present our findings at the Year 1 NSF review. So interesting enough, Okami is a Japanese word. It roughly translates to wolf, and it pays a bit of homage both to Japan, where the processor originated, as well as homage to us and having our Seawolf mascot. The idea is that suppose not everyone can get an account, say for Fugaku, or be able to use the largest supercomputer in the world's fastest supercomputer. They can come to Okami and ideally run tests and applications on this new A64FX processor. So up next, we'll kind of go into the breakdown of a computer cluster just to bring everyone up to speed if you're not up to speed yet. And kind of as follows: every cluster more or less has a login node. In this case, and for the case of Okami, we have one login node as a platform for which everyone can compile their work or submit to different compute nodes or log into other compute nodes, which kind of brings us to the compute nodes. For Okami, we have 174 primary A64FX nodes, plus 2 debug nodes for quick testing and proof of concepts. We also have some specialized nodes, such as an Intel Skylake compute node, a la what you'd find on Seawolf, a Thunder X2 node, which is another ARM architecture that comes with GPUs if someone wants to run, say, more machine learning framework ideas, and an AMD processor, a kind of more of a fat node, if you will, with 128 cores for rather beefy jobs. And each of these nodes are connected together with a high-speed interconnect, such as InfiniBand. And I'll pass it off to Jan to get more into some of the nitty-gritty of what our study entails.
All right. Everyone hear me clear? Okay. Great. Thank you, Ben, for such nice introduction. So before we get into the real magic here, let's begin with a basic structure of a compiler. So almost all of the modern compilers that we use today, let's see, GCC, Kang, Cray, IBM Excel, or NVIDIA, like they all have this very same compiler structure called Multipath Compiler. It essentially divided a large program into several small programs and process them, and it develops multiple intermediate steps, here, front end, mid end, and we have back end. So all this multipath takes output from the previous steps as an input. So essentially, it will require less memory. And one thing worth mentioning is that the backend phase can be detached. In fact, for many compilers such as Cray, NVIDIA, and even Fujitsu compilers, which is a local featured compilers installed on Fugaku machine, like I will introduce it in later as well, use LLVM compiler as their backend phase instead of using their own, or at least one of their version has used the LLVM. So with that in mind, let's see what we have actually on the Okami. So on the Okami, of course, we have the standard GNU Compiler Collections from version 8.3.1 to version 11, and also regular LLVM compiler collections from Clang 11, and we have Clang 12. And also we have a very special ARM-based GNU and LLVM compilers designed for ARM architectures. However, there's one thing I want to be clear is that even though like we say we have the ARM GCC, is actually just the regular GCC, but the ARM Clang is actually the special edition designed for the ARM architecture, which is really cool. Okay, and we also have the Cray compiler. It's a fantastic compilers, and we have the version 10.0.1 on the Fugaku, on the Okami, sorry. Of all this, only the regular LLVM compilers and the GCC 8.3.1 do not generate SVE instructions. All others, does. So let's move on to Fugaku. So on Fugaku, we have a special compiler called Fujitsu, and introduced previously. The latest version is 4.4.0a, and it's a feature compiler that works on both logging nodes as well as the computing nodes. And we also have the GCC compilers 8.3.1 and 10.1. And since we already know that GCC 8.3.1 is not going to generate any SVE instructions, so we will be only focused on the GCC 10.1 in the rest of our presentations. Okay, so with understand all those, having all those in mind, we start to think like how all these compilers will generate the SVE instructions, right? Are they all going to generate the same SVE instructions, or is it different? And are there any loops that maybe cannot be vectorized, or which compilers would have the best performance? Or let's see, which compilers would be the fastest, right? So it turns out the different compilers does generate the SVE instruction differently. To further demonstrate this, we have used one of the sample code from Tony. So thanks, Tony. And here it comes with the code. It's a very straightforward matrix operation program with two loops here and here. Let's see what compilers is. So on the top section, we have the Cray compilers, which clearly shows that on line 24 and line 25, the vector involved with the random function called drand48 cannot be vectorized. And the loop on the line 32 is vectorized. So back to here, so this is cannot be done, and this is vectorized. Okay, and in the middle sections, we have the ARM Clang, which is very interestingly, we can see this thinking bitcast, which means it's kind of casting between the single precision and double precision. That will be more, I'll address that more on the next slide. And on the bottom sections, we also have the GCC, and GCC shows that everything involved with this DRAM48 random functions cannot be vectorized, and the only one could be vectorized are line 32, which is matches exactly what we have seen here, right, on the Cray compilers. So to check, or let's see, to back up what we were seeing here are truly what has been generated. We also screenshot the exact instructions has been generated with different compilers. And here we got like GCC, ARM plain, and Cray compilers on the Okami system, and also the Fujitsu compilers results on the Fugaku systems. So we can see a very similar results between the GCC and ARM plain, that they all did this format conversion steps here, like taking the single precision to the double precision and back to the single precisions, which verifies what we have seen here, right? So, but it seems a little different with the Cray compilers, actually. The Cray compiler seems to ignore the format conversion steps. They're just kind of assume that it to be single precision and from the very beginning, which for me is very quite, I would say, like a little like very smart to do that, because if a compiler has this ability to assume things, that might lead a better runtime performance, right? Or it might save us more time. But what really impresses us is the results we're getting from the Fugaku systems. We can see there's it's actually, it generates, the Fujitsu compiler generates a lot more instructions, SVE instructions, compared with all the other three compilers on the Fugaku system. Due to the space limitation, we just put a portion of it, but trust me, there's a way more than this on the Fugaku machine. So with understanding all this and knowing all that, I think now is the time for us to really experiment some actual scientific benchmarks or applications and see the actual see how the actual performance is. So for us,
yeah, and I'm sorry to interrupt. But before you go on from slide 15, can you explain what's going on the Fujitsu compiler? Is it somehow unrolling a loop more extensively? Why is it generating so many instructions?
Yes, that's actually a very good question. We actually still trying to investigate why they're having that much more instructions, but it's partially we're thinking the reason is because the SVE operation rate is very higher than those other compilers. Maybe they have structured their compilers in a different way. So, but that needs a further analysis. So,
well, thank you.
Thank you. Okay. So yeah, we have choose two different scientific benchmarks to testing this. One is called SWAM, and one is called Pennant. And Ben will continuing on with introduce you guys with Pennant for SWAM. So yeah, SWAM. SWAM is a pure OpenMP and Fortran-based benchmark. It essentially is a weather forecasting model that's solving differential equations by using finding different methods. Well, in other words, it's just matrices, right? So it comes, the entire package comes along with several different sample problems. And in here, we choose the largest size called ref. And here are the detailed matrix size and the iteration numbers. We have tested with the three compilers. One is ARM Twang, ARM G Fortran, and Cray Fortran. So, and here comes the results. As our expected, or as what we have saying, that Cray gains the fastest performance. And even take example for the single-threaded case, we can see like Cray is almost 70% faster than the GCC, which is very, very impressive. Since like Cray could tends to assume things or having this special abilities, then this is all very good but understandable, right? So yeah, and come up with comes to the speed up and efficiency study, and things a little different. We can see here GCC and ARM plain actually have the better speed up ratio than Cray compiler. and that could lead to the efficient study shows that Cray compiler is not as efficient as GCC and ARM Clang, and they have a general trend to decreasing. Part of the reason might be the runtime overhead, meaning that if we're using more OpenMP threads, they're causing more communication time between each other instead of the actual computational time. Okay. Yeah. In order to, oh, sorry.
No, maybe you're about to ask my question, but I mean, so I mean, in addition to overhead, you could hypothesize that since the Cray code was running more efficiently already for just a single thread, that maybe it's already utilizing memory bandwidth more. So yeah, maybe the Cray is saturating memory bandwidth. So have you looked into some of the performance profile, bandwidth usage, cache misses, and things like that?
Yes, exactly. Great questions. I will just about to introduce our profiling results.
Oh, very good. Thank you. Sorry.
Yeah. No, please. Thank you. That's very good. Yes, as you mentioned, that could be maybe they're already efficient enough. So, right. Okay. Yeah. So to further analysis the cost and the cost of the SWIM and what exactly going on with the SWIM benchmarks, we have used a special tool called ARMMap. Come along with the ARM Forge collections, and it is essentially a unique profiler that helps developer to see the cause of slow performance by measuring the computation time, the thread activities, synchronization, etc. And in SWIM, we have choose two thread number cases to show the differences and showing why the efficiency study is that. Okay, next slide. We are first using the we're first profiling the SWIM with 12 OpenMP threads. Why 12? Because like 12 is the maximum capacity of one core memory of group. So in this case, we have achieved 95% time in the OpenMP regions, which is not surprising at all, because since this is a pure OpenMP benchmark, so it's pretty straightforward. And the computational time took about 90%, is very high. And runtime overhead is only about like 9%. So it's relatively efficient with small numbers of OpenMP threads. And on the CPU matrix, we can see the computational almost took like 100%. The I/O is as low as it could be ignored. Like it's very tiny. So it's really good. And the main memory gigabyte is 6.3 as expected with the matrix size. And then next, we have the full capacity of the entire A64FX chips tested with 48 OMP threads. So that brings the total time to 96% of the time. But with this increase, we can see actually a computational decreasing around like 71%, and the runtime overhead increased to 30%. So that could kind of verifies what we have seen in the efficiency study, right? So and the CPU matrix here shows as well a little bit decreasing on the computational time, tiny increase on the I/O, and the memory is still 6.3 gigabytes. Not perfect, but fair enough. Okay, let's get on to the Fugaku. So we have only chosen two compilers to run SWIM on Fugaku. One is called GCC, and one is traditional Fujitsu compilers. With both with SVE instruction enabled. And one thing I want to explain before we jump into this exciting result is Fujitsu compilers actually has two mods. The one mod is the traditional Fujitsu compiler, which we use here. It's the backend is just its original, and there's another one with LLVM backends called Fujitsu-LLVM. But since there's no Flang compiler installed on the Fugaku, so in here we can only just use these two. Hopefully in the near future we can test all three then. Okay, and also one additional thing we want to say is in order to achieve the best performance of the Fujitsu compilers, there's a very special environment variable we need to taking care of. It's called paging policy, and that is environment variable controlling the memory allocation, which is crucial for the for optimizing the runtime. For anything like threads over 12, like if we're using, in other words, if we're using multiple core memory of groups, then it's preferably that we set that setting to be demand, demand, and demand in order to just place the data nearby the threads who has first touched it. And if we just want to test with a thread inside the single core memory of group, which means like anything less than or equal to 12 threads, then we can just use the recommended setting as prepage, demand, and prepage. And now we can see what we got here in this graph. Took the example of the single-threaded case, we can see Fujitsu compilers is almost 82% faster than GCC, which is superb. And well, even though we can see there's a little variance, and in the middle section there's a back and forth things like going here, that could partially explained by the insufficient like scaling, poor scaling situation of Fujitsu compilers targeting OpenMP applications specifically. It's a little bit unfortunate, but overall the performance is still like amazing. Cool. So yeah, back to the speed up study. As we shown before, it's here comes with a similar situation that GCC compilers has a better speed up ratio than Fujitsu compilers, and the efficiency study shows Fujitsu compilers is not as efficient as GCC compilers, which could be partially explained by the insufficient optimization, or it's already faster enough. So, right. Okay, let's move on. Since we have already showed all other three major compilers providing results on previous, so in here we were just using a special profiling tool called FEEP on the Fugaku system, stands for Fujitsu Instant Performance Profilers, which provides extremely detailed output. When I say extremely detailed output, meaning like 4,000 text lines. So I doubt anybody actually really want to read through all of them, especially when the majority of that are identical with what we have seen with our map. So in order to save us a little more time, I conclude like three different or facts from the FEEP with the SWIM. So first, SWIM has achieved 31 gigaflops on the Fugaku machine, which is relatively high compared with its size. And the runtime is about 3 to 5 times faster than the runtimes on the Okami Gnu compilers. And it has extremely high SVE operation rate, up to 99%, which this could be very impressive, or let's see, or this could indicate why that Fujitsu compilers is that good. All right, so with all that, I will give it back to Ben to introduce you guys about Pennant.
All right.
Okay, I'm Ben. Sorry to let me come in with a couple of questions. So that SVE operation rate, what is this? What is the rate that you get from the GNU compiler?
That's actually the problem, that ARM map or ARM tools does not give that information, unfortunately. So
yeah, we can get it from other tools. So
okay.
Yeah, so that would be a very interesting comparison. And then I've asked this question before, but maybe I can't remember the answer. So in the SWIM in a loop, now the GNU compiler is actually good at vectorization. We have some benchmarks where it beats the Cray compiler, but clearly it's doing really badly on this one. And my question is really directed to why. What is it about the inner loop of SWIM that makes the GNU compiler run badly?
The new compilers run badly. Well, I wouldn't say it run badly though. I just see I just want to say that Fujitsu compilers runs really good. In the comparison, GCC compiler does not give that great performance. Partially, I think the reason I definitely need to go back and to reanalysis a lot of things, but I think partially of the reason is showing is because like for the GNU compilers, the SV instructions only that much. There's not much SV instruction honestly has been utilized, and Fugaku on the Fujitsu compilers it generates way more. So a lot more instructions. Maybe that's one of the reasons I would guess. But I would definitely like go more deep in that. And hopefully could give back to this question like in the near future time.
Good. I look forward to learning more. Okay, great. Thank you.
Thank you. Yeah.
We also have a question from the chat from Oliver asking if Swim solves KDV.
KDV.
Uh,
I will I will give back on that on the chat channel if that is okay.
Alrighty. Alrighty. So let's jump into Pennant. So to start off, Pennant is a mesh physics application. So and from what I read from Los Alamos National Laboratory's description of it, it implements a small subset of flag physics. It's dominated primarily by pointer chasing and is designed for rather advanced architecture research. So that kind of plays as like a sort of foil to kind of what Pennant gets into, or what the A64FX is rather. So because the A64FX leans towards what I would think of as spatial locality and just a more vectorized instructions, pointer chasing kind of acts against that, and with memory kind of all over the place, it'd be hard to, I guess, like make things run more efficiently in some cases. And so that actually kind of takes down two things almost, that memory requirement as well as locality. And that actually partially jumps into the second section of, because the A64FX only has 32 gigabytes of high bandwidth memory on node, as opposed to say an Intel Skylake processor, or node on Seawolf with 192 gigabytes of memory on chip, for example, a large input will crash after about 2 or 3 minutes. And like looking at a mixture of like Linux's top command or top output, as well as seeing what the output is generated from with these larger inputs, the initial thread will allocate all this data kind of at once, and then as soon as this initial ramp up period ends, the next 30 seconds fill up all the on-chip memory as well as any extra Linux swap memory, and the OS sends a signal to kill the program. So there's only so much you can do on a single node with large memory. Another downside is this lack of, I guess, hardware thread availability. So the A64FX processor only allows for 1 hardware thread per core, compared to say Intel Skylake's 2 plus threads per core, or hyperthreading. Another thing that I remember Robert actually talking with me about a while back is the possibility of how the thread scheduling is set up. So OpenMP allows for static as well as dynamic scheduling, and changing how that might be set up with the OpenMP directives inside Pennant may affect the output. I haven't really gotten a chance to study it yet, but I'd really like to in the future. So in this case, we'll be focusing on 2 inputs, well, one of 2 inputs at least, Sedov big and LeBlanc big, both of which are non-trivial input sizes that won't crash after 2 or 3 minutes. In the case of, and particularly in this case, LeBlanc big, which is a structured mesh all square zones containing approximately 230,000 points and 460,000 edges, for anyone who's curious on what this input size is. So similar to Yan and Swim on the next slide, I also ran with the GNU Compiler version 10.2.0, ARM Clang++, and the Cray compilers. In this case, the Cray compiler pretty much takes the cake on every single thread, on every single OpenMP thread value we've given from 1 to 48. And the GNU compiler, for the most part, has this slight edge over the ARM Clang compilers, at least except for this one section at two OpenMP threads. Though because they're so close, it could be argued that the runtimes between these two may swap spots in some cases. But for the most part, Cray pretty much performs twice as fast, or almost twice as fast as GNU and ARM Clang. On the next slide, we also kind of go into relative speed up and efficiency. And surprisingly, with ARM Clang's linear, near linear speed up, it also correlates to having the largest relative efficiency with its inputs compared to this sort of battle that GNU and Cray the GNU and Cray compilers are having at around 24 threads, both in the relative speed up and efficiency. And so I'd like to see I'd like to devote more time to study what's going on under the hood with these, but unfortunately classes kind of get in the way from time to time. So on the next slide, we like Yan did, I also ran Pennant through ARM map and its performance profiling tools. And similarly, it spends a large amount of its time just performing computations in just 12 threads, all set up in one core memory group. So say cores 0 to 11, as opposed to being distributed across the memory groups. Conversely, on 48 threads, we see that pretty much a substantially larger amount of time is being spent on thread synchronization compared to computation, with a substantial amount more with pretty much the entire system load being used. With some of the other CPU metrics, kind of like Robert was alluding to earlier, this might help to explain some performance and efficiency. Or it'll help explain these performance and efficiency results. But again, I'd like to look into this hopefully before the end of the semester. On the next slide, we'll go into some measurements on Fugaku. So because Pennant is built around C++, I was able to use both this traditional backend and the LLVM backend. And I noticed this strange, comparatively strange result compared to what Yan found with Swim, where the Fujitsu compilers in both cases eventually lost in terms of raw runtime compared to just a standard GNU compiler, be it 8.3.1 or 10.2.0. I forgot to change the label on this graph. What's even more interesting is that at lower thread values, the Fujitsu LLVM backend wins in terms of raw runtime over the traditional compiler. And there are a couple of reasons for this from what I found. Reading the documentation, the traditional Fujitsu compiler seems to support only OpenMP versions 1 or up to version 3.0.1, if I recall correctly, whereas the LLVM backend supports more recent releases. So that could be one thing with the specifications. Another thing would be how each compiler is generating instructions to utilize the the on-chip bandwidth. And a few other things I I'd like to get into, but there's just already been so much from the performance reports that it's hard to specify one thing. Yeah, but I think it could also be that because Pennant is a hybrid application with MPI and OpenMP compared to a purely OpenMP application, that might get in the way. I'd like to look into that further as well. But in any case, on the next slide, we detail also similar relative speed up and efficiency between GNU compilers and the Fujitsu compilers. And what I find kind of interesting is that both Fujitsu compilers exhibit kind of near identical behavior, even though at different levels. So in the relative speed up, we see that actually all three compilers kind of exhibit this similar behavior with speed up until you have more threads than can be placed onto one core memory group. Talking with some of the research scientists at the Riken Center for Computational Science in Japan, one thing that was mentioned is that with Fujitsu compilers, the OpenMP does not scale well, and that could also be a cause of how it's specified, or what the specification is underneath the hood, so to speak. Similarly, this relative speed up also kind of gets reflected in efficiency with respect to each compiler, where the GNU compiler kind of holds steady after adjusting to having more threads across more CMGs, compared to Fujitsu compilers, where it just kind of decreases rather quickly. On the next slide, I also ran Pennant through this Fujitsu immediate performance profiler, hence the acronym FIP, particularly with the one OpenMP threaded runs. this one kind of just happens to be the most interesting just because of that large dichotomy we saw back on slide 31. With the traditional backend, we see a slower runtime combined with a smaller memory bandwidth saturation, but more CPU instructions executed per clock cycle. So what I'm inferring from this is that the traditional compiler is slowly kind of falling behind, so to speak, with having to work more, with trying to work more to get the same like raw runtime performance compared to the LLVM backend, which executes less than CPU instructions per clock cycle, but results in a faster runtime and larger memory bandwidth saturation, which is more or less kind of the direction we want to go. These runtimes, at least the runtime aspect, converges as we get to higher thread values, though the other performance metrics like memory bandwidth, SVE, instruction rate, etc., all kind of stay consistent as we increase to higher thread values. So next slide, please. Going into future work, we like kind of like what Robert was alluding to. We'd like to explore a bit of OpenMP behavior with Swim moving forward, along with why that inner loop could be could be detrimental in the case of GNU compilers. Because both Pennant and Swim only use a small subset of what OpenMP directives are available, I personally I'd like to analyze more of these directives. So like task-based parallelism, the effect of shared memory in tasks and in threads, and as well as in teams, as well as the effect of environment variables, both on Okami as well as Fugaku, and the allocation of variables through OpenMP. And then lastly, once we get, hopefully in the near future, once we have these Fujitsu compilers on the Okami system, it'd be interesting to see how the underlying hardware would affect outputs. So like, for example, Fugaku runs on a customized Linux kernel stripped down and a sort of customized high-speed tofu interconnect. Tofu standing for Torus Fusion, which is Fugaku's like sort of proprietary interconnect, compared to Okami's InfiniBand and just a standard CentOS Linux distribution. Lastly, here are some key takeaways. Essentially, the A64FX does allow for ultimately faster and more efficient application runs compared to its competitors. If not in the small case, then definitely at scale. OpenMP behavior definitely can be influenced by either by core and thread layout across memory groups, and or based on compiler specifications. And sort of more of a promotion for Okami, check out this website either through IACS or make sure to reach out to Dr. Eva Sigmund, who is the lead research scientist for Okami. And yeah, and so lastly, we've compiled a list of references just in case anyone's curious on where this all came from. Yeah. So yeah, thank you all so much for your time. Any questions? Awesome.
Thank you. And before any questions, I just wanted to give a shout out to Tony, who was very extensively involved in all this work. And I forgot to say that at the start. So yeah, so thanks to Tony.
Hey.
But I was going to get away with it.
Looks like Owen is raising his hand for a question.
So yeah, Owen, feel free to unmute yourself.
Yes, hi. Thank you for this presentation, which I could understand, even though I don't have any relevant background. So I very much appreciated your effort to reach out to a larger community in this talk. You mentioned in passing, one of you mentioned in passing machine learning, and as someone who uses machine learning a lot, is there any reason for me who's interested in using neural machine learning to use Okami at this point? Or are the main advantages that you talked about irrelevant? Because yeah, that's the question.
Yeah, so interesting you should ask. As far as I know so far, there's one we currently have a student in Dr. Chapman's lab, kind of working to I guess port is right, if that's the right word, port common machine learning libraries from like say Python's TensorFlow and Keras, among others, to the A64FX chip, and primarily because the A64FX chip has this ability of being able to work as well as its competitors without the use of GPUs. So it's a challenge in of itself that we're currently working on. Some preliminary results from the Riken Center for Computational Science in Japan have shown that some machine learning workloads do work to some extent, though I'd have to read the presentation, the papers and presentations that came out of it to get a better idea of it thus far.
So, Owen, let me jump in. I don't mean to use up Jan or Ben, but I think as Ben was saying that for machine learning right now, the Okami is interesting if you yourself are interested in the performance of the algorithms used for machine learning. Right now, we don't have a full machine learning tool chain on the machine, so it's probably a bit premature to get on it.
Thanks.
No problem.
Thank you.
All right.
I'm going to jump in with another question for you, Ben. And do you ever, given that this is Pennant is a pointer chasing benchmark, I'm a bit surprised that the Cray compiler is doing so great. I mean, do you have any sense about what it's doing that the others compilers aren't? I
think it kind of goes along with a few things, kind of like what you and Jan were talking about earlier, with the notion of Cray being able to make making certain assumptions to help optimize performance, as well as I guess already saturating memory bandwidth faster than GNU or ARM-Clang, for example. I don't remember off the top of my head what some of these performance metrics, some of these other metrics would result in, or why Pennant works so well with the Cray compiler. I'd have to look at some of my other work and get back to you on that, if that's all right.
Yeah, very good. Thank you.
Yeah, I just did want to jump in there because compilers don't make assumptions; they have to prove things, right? So another way,
right.
a slightly better way of saying, I know that you know it, but I just want to be clear. The Cray analyses are I think, especially for high-level code, are definitely at a different level than LLVM and GNU. So I'm assuming that yes, they're doing better analysis and deducing that they can streamline the code and remove instructions rather than assuming. So
yeah, very good.
Yeah.
Thanks, Dr. Chapman.
Yeah. And Jana, a question for you. So on one of your slides, you basically were showing that there was a plateau in the middle of the thread scaling that you were getting from the Fujitsu compiler. Like we get into your Fujitsu results. Yeah, maybe this slide is either this one or the next one. Basically, as you go from say 4 threads up to 16 threads, the performance is roughly flat, and that's kind of puzzling, isn't it? I mean, I can understand within one CMG why you might saturate memory bandwidth, but as you go from 12 to 16, now you've got a whole new CMG. So it's hard to understand.
Yeah, that's very hard to understand, and it's very interesting. In fact, when I did the experiment, I changed multiple settings of these environment variables, and the results changes even more dramatically than this. So after Ben has asked the people from Riken and being told that it's possibly because of poor scaling data towards to OpenMP applications. So hopefully there would be something to change in future, or I guess.
Great, thanks very much.
Thank you.
Well, I know I've asked lots of questions, and so any more questions from the floor?
Feel free to speak up. Don't we won't bite, I hope.
Right.
I guess, can I ask a question?
Go for it, yeah.
Okay. So I'm not familiar with the difference between swim and pennant, and I tried to understand, but I'm slow. So do you know what kind of computations they're doing that makes the different? Is that why certain compilers are better for swim versus pennant, or
That's a good question. I don't think I know the full answer. I don't think I know the full answer. I'm not sure what I know that Pennant leans more towards hydrodynamic computation, and that OpenMP kind of actually plays a bit of a rather small part in the application itself. It's mainly MPI based, so that might be part of it. Compared to Swim, which is purely OpenMP, and all the computations are done in just like 3 large loops, as opposed to how Pennant kind of executes its code.
Okay.
Sorry.
But Ben, you started off describing Pennant as a pointer chasing application, and maybe describing what that is would answer.
Okay. In what way? I guess in what way? If that makes any sense. Like, I'm not quite sure what you mean.
Well, how about just what is a pointer chasing application?
Yeah. Okay. Loop. Yeah.
Okay.
Structures. Yeah.
Sorry, Professor, you're saying?
It's okay. Just go ahead. Sorry.
So yes. So in this case, just to kind of explain pointers for anyone who's unfamiliar with them, in languages such as C and C++, pointers are effectively addresses that say, okay, like you've accessed me, but the data is over there, and it pretty much points to some location X in memory. And these pointers aren't necessarily all in some contiguous memory block. They can be scattered throughout the underlying memory. And so a pointer chasing application kind of goes against this idea of locality, where everything could hypothetically just be in one spot in memory where it can be easily reused, and instead just says, hey, I'm over here. No, I'm over here. And kind of jumps back and forth across the program's address space.
Also, unlike where Jan had set like this environment variable so that all the data is near the thread that touches it, Pennant kind of just points all over the place, I guess.
Exactly, yeah.
Oh, okay.
One part I do remember of Pennant's code is that that's the initial that part of the OpenMP directives are based on are centered around like the initial allocation of variables, and everything's done through this function malloc, which is C and C++'s way of allocating memory for these pointers, and it's not always guaranteed you'll get something in the same, like you won't get like say two memory blocks right next to each other if you call malloc twice. So that part is just kind of the operating system saying, hey, here's memory, go crazy.
Okay. Yeah, sorry for asking such a broad question, but thank you. That makes a lot of sense.
No problem.
Cool.
And there are, of course, multiple malloc implementations out there.
Yes, that too.
Will they do the same kind of thing like this environment variable, so you can malloc like different?
Well, the XOS one?
Yeah.
Oh, that's Fugaku specific.
Right, but like malloc could do different types of malloc could do different.
Yeah, there's different algorithms for how the different malloc manage the memory. They're usually called memory arenas.
Okay. Oh, thank you.
Yeah, and I guess just to chase up with that, it's a lot harder to compile codes that follow pointers too, especially in this context. So makes everything harder.
Cursed pointers.
Except when you need them.
Exactly, yeah. Essential but cruel. But
that's a good way to put it, yes.
Ben and Jan, thank you very much. Excellent, a lot of fun. Thank you.
Thank you.
Yes, thank you.
Great job, guys. Thank you so much.
Take care. Bye-bye.